Hi, everybody. My name is Kurt Munson. Today we're going to focus on a relatively high-level topic. This is not going to be a technical, super technical deep dive. This is an introduction to fatigue and durability. So over the next 45 to 50 minutes, we'll explore this concept of what is fatigue as a failure mode, and what does durability and fatigue analysis mean, and how does it help us as engineers produce stronger, more durable, and more reliable products. Before we do that, just as a reminder, Princia itself is, you could say, a couple of software brands, nCode and ReliaSoft, which many of you guys will be familiar with. nCode for the durability, fatigue, signal processing, and vibration analysis software, and ReliaSoft for reliability and maintainability and failure mode effects and analysis, FMEA software as well. Princia offers a wide range of software and service offerings in the arenas of reliability and durability. Today we're going to focus just over here on the right side, which is the nCode side of things. As a matter of fact, we're not really going to focus on software today. We're going to focus more on concept. So this is not going to be a webinar on how do I use a piece of software or how do I interact with a software tool. We're going to take a step back from that and think more conceptually here and think about things like, what do we mean by fatigue as a failure mode? And then once we've established that, we'll move into looking at things like what fatigue analysis or fatigue life prediction methods are available to us. And in this, we're going to look at three different methods today: the stress life method, also called SN, the strain life method, also called EN, and also we're going to look at a fracture mechanics-based method called crack growth. So we'll have an overview of the three of these, and we'll do some comparing and contrasting between these three to understand what does each one of them bring to the table separately, and how might we use them as engineers to help engineer or develop more durable and reliable products. The third item here, we're going to look at the application of fatigue analysis. So how might an engineer use these methodologies or these algorithms, either with measured strain gauge data, or by using a CEA-based finite element analysis and the stresses that come from that. We'll wrap up today with a case study where we'll be looking at how do we ensure the durability of a suspension arm for an all-terrain vehicle. We'll have a summary at the end, and at the very end, I'll be able to address your questions that, as Alex said, you can provide to me through WebEx's Q&A panel. So with this agenda in mind, and keeping in mind that this is, again, not a software-focused webinar, but rather a conceptual engineering overview, let's look at why are we here today. So that's not me down there in the lower right, but I'm just thinking this is us as engineers, kind of a collective body, someone thinking, why are we here today? Why are we talking today? Well, there's an awesome quote that you can see here from a very important machine design handbook, Shigley and Mischke, that's been in publication seemingly just about forever. A number of us use this book in our engineering education. The important quote here is that, essentially, just to paraphrase, if we don't understand fatigue, but we have to design against fatigue, we could just make the part a lot stronger. However, that makes the part more expensive and also makes it heavy and can lead to other problems as well. And the key is we need to get smarter, because engineers who produce these under-designed products are not marketable. So to be better engineers, we need to think about new tools and conceptual ideas, like not just designing with large safety factors to overcome fatigue, but to really understand what fatigue is and embrace the methodologies that allow us to predict fatigue lives, and then to further improve fatigue lives where necessary. Here are some examples of fatigue failures over the years, and I'm sure all of you can think of an example of something that's broken around you, whether that could be something as small as a toothbrush or maybe a garage door spring. Hopefully none of you have run into this scenario here, up in the upper corner here, where your airplane has gone into convertible or cabriolet mode. Or hopefully you've never been on a ship that's cracked in half. Or hopefully you've never been near a wind turbine that shed an entire blade, or a train that's crashed due to fatigue failure. Some of you may have experience with fillings cracking over time. Believe it or not, even dental implants need to be designed with fatigue in mind. Otherwise, they won't last the amount of time that I would like them to, and I'll end up with pain and have to go back to the doctor. So let's think now about what really is fatigue in terms of a definition. Quite literally, fatigue is a failure mode. And you can see here that we've got cracks starting due to fatigue loading. So fatigue is some kind of a weakness or lack of strength over time because of repeated loading. So to be very specific about it, in an engineering sense, fatigue is the initiation and then the growth of a crack, or growing from a pre-existing defect until that crack reaches some critical size. Critical size might be very small in some components. For example, in the crankshaft of an engine, a very small crack can be a very serious problem because the stresses are extremely high and we lack the ability to inspect a crankshaft when it's being used. On the other hand, quite long cracks might not be a problem. For example, in a sidewalk, I have very large cracks in my sidewalk, but the city doesn't care enough to replace that sidewalk in front of my house because it's not safety critical. So to think about this another way, if you think about other structural failure modes, static failure is not fatigue failure. Static failure is when we look at stress and strain behavior and the stresses become higher than the strength of the material. We call that tensile strength failure or static failure. Some people call this as well. Fatigue failure, on the other hand, is the stresses are never really that large, but they happen over and over and over again. This is kind of like saying static failure is like if I go to buy a Ferrari, I will probably go broke very quickly. In other words, I won't be able to buy a Ferrari. If I decide not to buy a Ferrari and instead say maybe I'll buy a sensible sedan or something like this, I can buy a car. I could buy several cars. If I buy enough cars, I will go broke. No single car will break me. So two very different failure modes, and chances are if you're working on a structural component, you have to think about both of these. We spent a lot of time thinking about this, about static failure, in college. Let's make sure the strength of the material is greater than the stresses that we put on it. But the fatigue failure mechanism, as we saw in previous pictures, can be very significant to things like bridges and aircraft and fillings in your teeth and wind turbines and bicycles and motorcycles and so on. So this is yet another failure mode we need to design against. Now the way we design against that is kind of laid out in this roadmap here. We need to understand some key inputs into a fatigue life prediction algorithm. And then the fatigue analysis takes place, and we get answers out of this. And we can use those answers to help interpret and understand things like, is our product going to last long enough? Or does it need to be strengthened in some way? Or can lightweighting come into play now because we've actually over-designed our part? The key inputs over here, things we need to understand critically, are number one, what causes cyclic loading to happen? Fatigue doesn't happen unless stress or strain changes over time. Something causes a change of stress or strain. This might be due to thermal loading in the case of a bridge. It might be due to wind loading in the case of a bridge or an aircraft. It might be due to, say, road loads or engine vibration in the case of a car or a motorcycle. It's critical for us to understand that. Secondly, we have to think about geometry. How does the load acting on our part become stress? And as the load changes, the stress changes and can lead to fatigue. So stress concentrators, sharp edges, smooth radii, all these geometric details become very important in understanding the flow of stress through the part, which will govern the fatigue life of the part as well. Lastly, down here, we need to understand as an input material characteristics. We all know that aluminum and steel, for example, have different strengths in a static sense. They also have different strengths in a fatigue sense. Some materials will last longer than others, and even to be more detailed, even certain types of aluminum will last different lengths of time than others. Very small changes in alloying and heat treating and production and such can lead to differences in material strength, which lead then to differences in fatigue strength as well. All of these inputs then come into a fatigue analysis, and we'll look at different fatigue analysis methods in a minute: stress life, strain life, and crack growth. And these allow us then to predict how long will our part last. So this is the roadmap we're going to use today. Now to think about this physically, what actually happens in a microstructural sense when a fatigue crack begins? So we have to keep in mind that deep down in the material we've got these grains, and these grains have atoms and molecules packed together, and those grains can contain defects dislocations, preferred slip planes because of improper molecular packing and such. Fatigue really starts down in that microscopic level, and we can have this concept of fatigue damage occurring on a microscopic level because of material discontinuities. And over time, that crack that starts on a microscopic level, to the level that's far smaller than most engineers prefer to work at, over time that crack can grow from being microscopic to macroscopic. And you can even see that something caused the crack to start here. This is a tensile specimen that was cycled repeatedly, and now we're looking at the failure surface. You can see the crack started here, and the crack grew and grew and grew, and then finally the remaining area here was too small to keep track of the resulting stress, or the material is brittle enough that we had fast fracture occur. So we have to think about this as a microscopic phenomena, but yet we have to think about it also in a macroscopic way, because microscopic cracks may not be our problem, and to be honest, we may not be able to understand stresses at a microscopic level. So we need to take this up to a macroscopic level, and that leads us into a couple of different analysis methods. We're going to look at three methods today. The first being stress life, which says that stress drives the crack. Stress is the damage parameter. This works very well for high cycle fatigue. We'll also talk about the strain life method. Now, when the strain life method was first introduced, SN was already taken. So instead, the abbreviation of E, epsilon, meaning strain, the EN abbreviation is used. EN and SN are very similar, except strain life says that what drives fatigue cracks is not stresses, but rather changes in strain. And we'll see this in more detail in a little bit. The value here is that this allows us to model plasticity, which in turn means this works for low cycle and high cycle fatigue. Now, once we have an initiated crack, a good size, what we'd think of as engineering or macroscopic crack, a couple millimeters, so much larger than grain size, now we have to start thinking about a different mechanism that drives the crack from that point forward. A large, relative to grain size, macroscopic crack is driven by what we call stress intensity factor. We'll define this later today. And that allows us to look at how does this crack march along and finally lead to fast fracture. So these are the three methods we're going to look at today. We're going to start by looking what the SN method brings to the table for us, try to understand what it does, how it works, and critically understand where can it be applied and what are its limitations. So the stress life method, or the SN method, is built around materials testing to build the SN curve. So this particular plot here, this is stress range, in other words, how big is the fatigue cycle, and down here is the number of cycles to failure. So if we took this little material coupon, much like you'd use for a tensile test, but instead of just pulling on it in tension, now we're going to cycle it. So we have a push-pull, 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 as you can see, drawn down here in this sinusoidal waveform. Now, over time, this microscopic damage will begin, and the crack will start, and then this part will fail. So we write down on this plot, we have one of these red dots here is what was the stress range, how big was the stress cycle, and then how many cycles did it last. And we may test, say, around a dozen or 15 or 20 of these samples, some of them at repeated stress levels. You can see we actually tested 4 parts. We broke 4 separate parts at the same stress level to look at an idea of scatter. And we end up with this relationship in here. These dots all indicate that as stress increases, life decreases. And we can even curve fit this. This is usually done on a log-log plot. So we take the log of stress range and the log of the number of cycles to failure for each of those samples, curve fit that, and we end up with the SN curve. So instead of an SM family of points, now we have a mathematical relationship, like a power law relationship, indicating that as stress goes up, life goes down. Now the way that's used is really pretty simple. 2 ways. Number one is, if we know how big the stress cycle is, how long will it last? So this is to say, maybe for a given part, we know that the stress cycle size is going to be 300 megapascals. For this particular material, it says that 300 megapascal cycle can be repeated on the order of about, it looks like just under 10,000 cycles to failure. Keep in mind this is a log-log plot, so that's probably on the order of 7 to 8, maybe 10,000 cycles under that stress range. So if a designer says, hey, we've designed this part, the stresses are going to be fluctuating around this range, we can use this SN curve to answer how long we predict it will last before it cracks. We can also turn this around to say that if the part needs to be designed to last X number of cycles, what's our design stress? In other words, think maybe, for example, with a part that's in an engine, it maybe needs to last 100 million cycles, is the equivalent of driving for 10 years, something like that. We could say that number of cycles, what's the allowable stress range? We can then take that to the designer and say, make sure we build a part that has the stress below this level so we can have a good chance of meeting our fatigue life expectation. So that's the SN curve in the SN approach. In general, we use this for high cycle fatigue only. And the reason why is that now we're going to take a look at the strain life method, which is similar but includes a nonlinear material model. It models plasticity. One of the challenges of the stress life method is that it's been around for a really, really long time, and as such, it never was built on a plastic-based material model. It's built solely on an elastic linear material model. Strain life, on the other hand, was built, you could say, was invented, so to speak, or was really developed after the understanding of material stress-strain behavior, including plasticity. So the strain life method captures plasticity and then brings some new things to the table for us. So let's investigate that now. So the strain life method, we have to keep in mind, says that strain really is the driver to fatigue, not stress. Okay, stress life method says stress is the damage parameter. Stress allows us to predict how much this is going to hurt. Strain life says, no, it's actually strain. And the reason why strain makes sense is if you think about, on a microscopic level, you can think about the material structure as a deck of cards. And as we cycle back and forth, it's like we're shifting that deck of cards. And once we stop cycling that deck of cards, we've got some microplasticity. This is the start of a crack. Now, this is far smaller than most engineers prefer to work with. On a microscopic level, though, we can actually see this, the start of this microscopic crack. So really, when you think about it, what's a key indicator of how disarrayed that molecular packing is, that deck of cards, so to speak, is, the best indicator of that disarray is not stress, how we pushed on it, but strain, how much it was deformed. So really, using the idea of strain as the driver of fatigue is a fundamental breakthrough and brings a lot to the table. Stress life, in its linear elastic material model, only works when stresses and strains are linearly related, which is high cycle fatigue. Strain life, on the other hand, we're tracking the right parameter, strain, and as long as we bring to the table a nonlinear material model, which is easy to do, then we can now begin to think about predicting fatigue life under elastic and plastic conditions. So let's look and see how this fundamental breakthrough of strain life helps us. Once again, we have material coupons here that we're going to be cycling under strain control conditions. We're going to break a series of them. Again, each one of these little red dots here is a broken sample. So typically we have, say, between 1, 2, maybe 3 dozen samples we break at different strain levels. And then we can do a curve fit then to fit the log of strain cycle size, strain amplitude, and the log of number of cycles or reversals to failure. Quite literally, the EN curve looks like this. It's actually built behind the scenes by doing 2 separate curve fits, one to fit the high cycle fatigue behavior and another to fit the low cycle fatigue behavior. So actually, you may not pay much attention to this, but the strain life curve itself is built on this, you could say, double power law with 1, 2, 3, 4, 5 parameters that come from strain life testing that now relate how big is the cycle to how long will it last. So this is what the strain life curve brings to us. Essentially, the stress life curve is this blue line, but the problem is the blue line with its linear material model doesn't follow low cycle fatigue. So in the end, if we have a low cycle fatigue problem, the strain life curve is really what we ought to be using. It brings a lot to the table for us. Now let's think now about not just how does a crack grow, but this time think about, excuse me, not how does a crack initiate, but rather this time about how does a crack grow. So the question is, if a crack does initiate here because of some combination of high stress and maybe some material defects in that region of high stress, if that crack starts there, now how will it grow? Or to put this another way, once a crack is started, how much time do we have to watch this crack grow progressively before we have this bang and fast fracture occurred? Or to put this another way, not just how much time, but why is it that this crack grew from here to there before fracturing? Why didn't that crack continue to grow even further? Or for that matter, are there some materials that would be susceptible to this crack starting but not growing very long before an even small growing crack becomes fast fracture? So now we're going to introduce this concept of stress intensity factor and crack growth rules. So the challenge of working with a crack or a crack-like flaw is that essentially it's nature's worst stress concentrator. As engineers, we design things to have smooth radii. We try to avoid square corners, for example, sharp changes in geometry, because we know that those lead to high stresses. A crack is essentially the worst ever stress concentration. It's like a circle with a radius disappearing to zero. So when we do that, or when we have this scenario of a sharp crack, the challenge is that we really can't calculate the stress on it because elasticity theory would say that an infinitely sharp crack has infinite stresses on the crack tip. So the stresses on the crack tip become very complex, and instead of looking simply at stress, now we introduce a new parameter, new to this world of fracture mechanics. We call this the stress intensity factor, and we give it the letter K. Now numerically, it's equal to a function of the nominal stress on the cracked geometry. This Y is the geometry factor. This A is how long is the crack. So in other words, it's not just P over A any longer, or My over I, or T over J, the kind of usual stresses you might have thought of from mechanics class. Now the severity of the stress on the crack tip, so the stress intensity factor, is actually a function of crack geometry, of nominal stress, and of how long the crack is right now. Now the nice thing is that this K here, stress intensity factor, it'll tell us things like, is this crack going to fracture immediately? Or is it going to hold steadily? Or if the stress and the loading begins to change cyclically, like fatigue cycling, is the crack going to grow progressively? So by working with stress intensity factor, we can start to answer this question of when does fast fracture occur, now or later? And if it's later, how many cycles later will it happen? Now, how many cycles later comes from a crack growth curve. So this is a little bit more complicated fatigue curve. What we have here is how big is the cycle. This is called, down here we have how big is the cycle. This is stress intensity factor range. So stress intensity factor that changes over a fatigue cycle. In other words, how big is the applied loading and the stress on the crack. And on this vertical axis now, this is what we call the material crack growth rate, DADN. So to be very specific, we call this plot a DADN delta K curve. How much is the crack growing per cycle as a function of how large the stress intensity factor range is of that cycle? So we could literally look up and say, for a crack that's a certain length with a nominal stress that changes by this much, for this material we can look up and say, oh, the crack is growing 10 to the minus fourth millimeters per cycle. As the crack gets bigger, stress intensity factor range increases, which means the crack growth rate increases, and we have this kind of a positive feedback mechanism that continues until finally we exceed a material fracture toughness value, material strength parameter here that is either very low for brittle materials or very high for ductile materials. So in doing this, this helps us now understand not just how does a crack start, but crack growth brings to the table the question of when will the crack progress to the point at which brittle, unstable, fast fracture occurs. Now, I want to shift gears a little bit here and think about how we can understand different types of fatigue loading. So far, everything looked at so far has been, if a cycle is this size, how long will it last, either until a crack initiates or until that crack propagates until fast fracture. So we've been looking at this type of loading up here, which we call constant amplitude. Next level of complexity in loading is what we call block loading, which might be something like this, where we have a certain size of cycle for some prescribed number of cycles or amount of time, and then maybe smaller cycles and maybe larger ones. Realistically, though, we need to be able to deal with this one. This is the most complicated one, and we need a way to deal with it. We call this variable amplitude loading because the amplitudes of the cycles are constantly changing over time. Any measured loading or strain on your actual engineered part will look like this, what I might sometimes call a squiggly line. Stresses varying drastically, strains varying almost randomly. I won't say random, but obviously a very broad spectrum of different size cycles. So what we're going to look at now is how do we extend from trying to look at fatigue in the sense of under this cycle, how long will it last, to under this massive combination of different size cycles, how long will the part last? So the way we do this then is we need to start thinking about the two critical aspects of fatigue cycling are, number one, what's the cycle size? In other words, how much does the stress or strain change? Peak stress alone is not enough to tell us about fatigue cycling. We need to think about what causes the stress or strains to vary. And when that happens, how big are those cyclic stresses or strains changing? And secondly, we need to think about cycle count. How often does this happen? If we're thinking about something, say, that's mounted in a helicopter that sees cyclic loading from prop wash from the rotor, that probably happens several times per second with the right, with the cyclic revolution of the blade. In an engine, we might have something happening hundreds or even thousands of times per second because of engine combustion and vibration and such. If we're looking at a civil engineering structure like a bridge, one of the killers of a bridge often is thermal loading, where we have a high solar load on the top and maybe cool air on the bottom. Now that could make a big stress cycle, but it's not going to happen very often. So that might be, the cycle counting might be at most one cycle per day, and if it doesn't get sunny one day, then that cycle doesn't happen. So we, again, have to think about for our part, what are the size of the cycles that occur, and how often do they happen? Now that ties in directly to a monetary analogy that I like to use here. This is like your life. If we have a pile of money, we need to spend it in various ways because that's kind of what capitalist life is all about. We have to spend money on things, right? We have to earn and we have to spend. If the amount of money we have is fixed, in other words, if we go to the bank and we have just some amount of money sitting in there we can use, the key things to figure out how long we can expend that money until we're broke is how much do we spend at a time and how often do we do this? I mentioned before that I can go out and attempt to buy a Ferrari and I'll go broke immediately. Or I can go out and buy, say, a whole fleet of motorcycles. If it's a really big fleet, I'll go broke. If it's a smaller fleet, yeah, I could probably buy maybe dozens of motorcycles. If I buy thousands of motorcycles, I'll go broke. So just like fatigue cycling, size and cycle count matter, same goes also as well for a bank account. Now, how does this work for a bank account? We call this Miner's rule, or in Europe, this might be referred to as Palmgren Miner's rule for linear damage accumulation. It says that if the cyclic loading is these medium-sized cycles, followed by these small ones, followed by these larger ones, Palmgren Miner's rule says that each one of these hurts. As a matter of fact, they don't just hurt by themselves. Together, the combined pain or the combined damage from these cycles is greater than the damage of any of them by themselves. To put this another way, this might be me buying lunch, this might be me making car payments, and this might be me making house payments. I will go broke because of a combination of all those. My house does not make me broke. It's the combination of all my expenditures that makes me broke. So quite literally, Miner's rule is this guy right here. It says that the summation of something, the summation of, we call this damage, summation of damage will cause failure if that sum becomes greater than 1. Now, to be very specific about how this works, let's take a look at this example. Let's say we have this particular material curve. This is an SN curve. We have 6 cycles at a range of 100 megapascals. So we go 100 megapascals, it says if only these cycles occurred, it would last for this long. Now, we also later have some cycles at a range of 80. If only those cycles happened, it would last longer. But these guys here with a range of 140, if only they happened, it would happen a smaller number of times. Now, we can't add those lives together. That means that the more different size cycles we have, the longer it will last. That doesn't make any sense whatsoever. So that the crucial genius of the Palmgren minor damage rule is to say that not adding up life is what matters, but adding up damage is what matters. So we had 6 cycles occur out of a total that could have occurred off this SN curve 88,000. So we're 6/88,000ths of the way towards failure just by cycling this way. We're further 12 1/millionths further by having these 12 cycles occur, and further 6,000ths of the way towards failure based on this. Add these together, we get 6 times 10 to the minus 3. We hope that fatigue damage is a nice small number, because if that approaches 1, that means our life budget is used up. In our case here, fatigue damage is about 6 times 10 to the minus 3, which means then this thing can be repeated over and over and over again, each time accumulating a damage of 6.8 times 10 to the minus 3 until fatigue damage equals 1. So to be quite literal about it, this says mathematically that fatigue life is actually the reciprocal of total damage. So if the fatigue damage is 6 times 10 to the minus 3, then the reciprocal of that is about, I think, 160, which means then we could reproduce this whole thing 160 times before the cumulative damage becomes 1, and we'd expect a crack to cause this to fail. Now let's look at how we apply this as engineers. So fatigue algorithms are neat. What's even neater is when engineers can use them to make parts stronger or to justify their paychecks. So we're going to look at 2 routes here. One is the measured strain route, like we see here. Here's some kind of a structural member, and it's got a strain gauge on it here, so we can understand how much strain and stress this part develops when it reacts, loads, and is used. We're going to look at the second approach here too, which is finite element model based. Exact same structure here, just that rather than building a physical prototype, we're going to be using a finite element solver to understand how load becomes stress, and we'll be using nCode to figure out how does stress become fatigue life. So we're going to look at this example first, and then we're going to move on to look at this one second. So let's review the concept of fatigue analysis using measured strain data. Again, here's another strain gauge, and I'm sure a number of you guys are familiar with how strain gauges work. HBM is a producer of all kinds of strain gauge-based transducers like this, which are key enablers to the concept I'm trying to describe in this particular slide. So the idea here is that we're going to build a prototype part, and then we're going to instrument it with these strain gauges in critical areas and measure this strain over time, and then use this to predict fatigue life in critical locations. And I'll show you how to do this using nCode software in about 5 minutes. The upside to this is that strain gauges have been used for probably about 60 or 70 years, about 70 years now. So they're historically accepted, and a lot of companies are very comfortable doing this. It's a documented engineering approach, well understood, and these gauges are nice because they measure change in stress or change in strain, whether the input is from dynamic or vibration loading or thermal or hundreds of cycles per second or a cycle per day with a heat up and cool down cycle on the bridge. These measure physical quantities like that. Now the downside is that number one, we have to build a prototype, which these days in terms of trying to be quick to market and cheap to market, building prototypes is expensive and slow. We need to make sure we place these strain gauges with care. In other words, we have to have some a priori knowledge of our entire structure. Where might fatigue cracks be more prevalent or growing earlier in life? That may come from experience or from FEA and such. If the design changes, the resulting strain data becomes less useful. And like I said, we have to have a working prototype to measure this on. So this approach we're going to look at in just a minute. We're going to process some strain gauge data in nCode here in just a second. Before we do that, though, I want to introduce The second approach, which is to use finite element derived stresses and strains, you recognize up at the top here, this is a virtual model of a piece of landing gear from an aircraft landing gear structure. So no prototype necessary here in this case. So instead of using a prototype and measuring strain and inferring stress from it, we are actually going to use a virtual model here and use finite element analysis to understand how load or vibration, acceleration, whatever the input is, into our part becomes stresses and strains. Then think about virtual stress cycles and predict fatigue life for this whole model. Advantage to this has been a game changer over the last, say, 20 or 30 years, is being able to understand how a part responds without having to build a physical prototype, which means then it's really easy to assess design changes. So if we were to add a stiffening rib here, or if we were to change this radius, or if we were to lightweight and remove a little material here, how would that change stress? And further, how would that impact product durability? FEA has been around for quite some time, not as long as strain gauges have been used, but it's still a well-adopted engineering tool that's recognized and respected in almost all industries. And of course, we can use a wide variety of FE solutions: linear, nonlinear, dynamic, modal, thermal, transient, and so on, as ways of understanding stress. Now, the downside to this approach is that it relies critically on FEA's ability to predict stress or to predict strain. In other words, as we've said through all these damage models, stress life, strain life, and crack growth, all of them rely on some type of stress or strain type input as the damage mechanism, the driver of fatigue. To turn that around, to put that a different way, given that that's true, if the stresses are either improperly measured using strain gauges, or if they're not properly modeled using FEA, we'll have almost no ability to predict fatigue life. So getting a proper understanding of stresses and strains before the fatigue calculation is really critical. And that can be hard sometimes in the FE world. There can be some very nonlinear, complicated multi-physics loading scenarios, for example, that lead to very complicated stresses. And we need to be able to understand those to be able to predict fatigue life appropriately. So let's do this now. Let's look at a little case study. Let's put these concepts into engineering action. So let's say we're designing an all-terrain vehicle like this, and specifically we're working with a suspension member down here. And the key is that in the customer's hands, this ATV is probably going to see some very abusive loading. It's going to probably see a lot of rough terrain. It could see jumping and severe bumps and this kind of thing. And we need to ensure that our suspension arm is strong enough to survive 2,000 laps. Now, I'll show you what I mean by a lap in just a minute, but just in terms of a design requirement, the statement of requirements here says that the suspension arm must be strong enough to endure, without visible cracks, 2,000 laps of our customer use case. So what we've done, just to give you a little background, this is the suspension arm itself here, and we have a physical part that was made. We're going to look at the strain gauge based approach first, and then we'll move ahead into looking at the finite element based approach second. This is the physical part, and we were concerned about 5 possible failure locations. We were concerned that the stresses would be high here, or maybe on the back side, or down in this way, or inside this pocket, or down back this way where the bushing and the arm come together and loads are reacting with a little bending there, that kind of thing. So what we've done is we've instrumented those 5 areas with actually applied strain gauges in those areas and wired them to our data acquisition box, which HBM produces an awesome array of. So HBM is here on to provide us with strain gauge and data acquisition hardware. And now what we do is we go out and collect strains in the field. So this is one lap of someone driving on the field. And now we want to know, how can we ensure that the suspension arm is strong enough to survive that 2,000 laps? So I'm going to switch out of PowerPoint, and we're going to look at using nCode software now to make some of these predictions. So let me just jump out of here, go over here to nCode. And a number of you guys have probably used nCode software before. If you haven't, you'll have to just take my word that we've got a lot of tools in here related to vibration and durability and fatigue analysis and such. We don't have time today to get into how to use the software, so I'm going to focus just on the higher level message of how do we interact simply with the software and then dig deep into the answers. So what I've got here is some measured time series data. I'm just going to drag that in here. These are the strain histories for those 5 locations. So we had 5 hot spots we were concerned with and that we strain gauged on our physical part. You can see that the strain sometimes vary quite a lot. I don't know what the driver was doing here, but something quite abusive, I would guess. And other times the strain levels are quite low. The process here has been built around a strain life cliff, and I've chosen to use a strain life cliff here because the magnitudes of the strain I know for a fact are quite high and may cause small amounts of plasticity, small amounts of yielding in our part. And as a result, then you may recall we said that the stress life method doesn't work with low cycle fatigue, whereas strain life works with both high cycle and low cycle. So I'm going to take advantage of strain life's ability to work with high and low cycle both and use that algorithm here. I'll just take a quick look into this process here. This glyph has properties that allow us to configure how it works. What's most critical here is on the Materials tab. This is in like a library of fatigue curves that nCode provides with the software. So we have a whole family of stress life curves, strain life curve, crack growth curves, and such. Tons and tons, especially, of stress life and strain life curves. So I simply can pick a material off this list like this, and then I'm going to go run this process. And it's going to go off and do some things in here. It's going to do cycle counting, calculate damage per cycle, use Miner's rule, and it's going to give us some answers here. So what we see up here, we have some answers like, let's see, we have 1, 2, 3, 4, 5 different locations, right? 5 separate strain gauge histories from 5 separate possible hotspots on our control arm. And this is telling us how many cycles were counted. This is total damage, so this is the result of Miner's rule being applied to the fatigue damage from each of these thousands of cycles. Here's how much damage is caused. Ultimately, what we have over on this side is life in repeats. Okay, and this means life in repeats of this measured time series data. Now, you don't know this because you weren't around, but this is 1 lap of a proving ground. And remember, our design guideline is the part needs to be able to survive without initiating a visible crack. It needs to be able to survive 20,000 laps. So this is saying actually that the life varies from the hottest spot is about 5,000 laps. This one's at about 10 or 11,000 laps. Here we're in the 800,000, 1 million, and 1.3 million. So some of these locations are really not going to be fatigue critical to us, but we've got 2 spots here where the fatigue lives are actually quite short, quite a bit shorter than our statement of requirements. So we have a problem. So we know for a fact that our part, as produced, our current design is not going to last long enough. Okay? Now, these plots down here, this is the rain flow histogram of how many cycles of what size, and down below is the damage histogram, which is how many of those cycles that were experienced, how much did they hurt. So the difference between these two here is this is cycles coming into the strain life curve, and this is damage coming out of the strain life curve. We can use this as a diagnostic to further understand, is this problem caused by lots of repetitive small cycles, caused by a few very large cycles, and that maybe allows us to redesign in a more pointed way. The key is, though, to recognize this up here. We have a couple of locations where the stresses and strains are just so high that we're looking at premature fatigue failure. So we need to think about a design improvement here, a design modification. Now, in my experience, I found I can't really very well go to a designer and say, the fatigue life needs to be improved by X%. Sometimes I get blank looks when I do that. So what's more important is if I could go to the designer and say, if you were to reduce the stress by Y%, then the fatigue life requirement will be met. So what I've got here on this second tab, this tab is called stress reduction. This is looking at the same strain gauge data. Here we have the same strain gauge data. This calculation, though, this time, let's look at its properties. It's got the same materials data as I picked before, same fatigue calculation properties, except this time I'm telling it, I want this thing to last 20,000 laps. Each of those locations, to what extent does the stress need to be reduced, or could even be allowed, if it's a cold spot, to increase to meet that life target? So I've kind of turned the life calculation on its head here. And now when I run this, it's going to take a little bit longer to run. But what I get out of this is, notice that, again, 5 locations. The fatigue lives and the fatigue damage are recognizable numbers. They're all 20,000 laps, plus or minus a small tolerance that the iterative backsolver uses. Here's the critical stuff. Stress reduction percentage. This says in this location, which was down by, I think it was about 5,000 cycle or laps to failure, so we're quite low in terms of fatigue life. This says we need to reduce the stress by 25%. In this location, we need to reduce the stress by 14%. In these locations, actually, we can allow a stress increase by 80, 100, and 130%. So if we were looking to lightweight, we have 3 areas we could lightweight and allow the stresses to go up quite a bit. But we've got 2 critical areas here where we need to reduce the stress significantly. I can take this to a designer now and say, hey, look, let's think about changing radii, increasing thickness, maybe adding some webbing, something like that. So in this area, the stress reduces by something on the order of about 25%. Okay, so that's our design improvement, you could say, kind of our guideline. Okay, so we've got actionable information. Now we can take that and redesign the part. And let's say now that that part has been redesigned. And as a matter of fact, before producing any prototypes, we want to look at this part and make a prediction of whether it will last or not. Okay, so rather than committing to any kind of prototype and testing and such, what we're going to do now is we're actually going to take a look at this part right here, virtually, and use FEA and FE-derived stresses to best predict if this part is even worth producing a prototype for. Okay, so here's our redesigned suspension arm, and maybe it's been beefed up in this area, or maybe it's increased thickness down this way or something like that. Whatever those critical areas were, we've reduced the stresses by that, whatever it is, 25-ish%. Now, this process looks very similar to the one we ran in the previous workspace, except now this is purely virtual fatigue going on. So I'm going to go ahead and run this now. This is going to take a little bit longer because it's actually not calculating fatigue in 5 areas. It's actually doing the entirety of the FEA model. So what's happening here behind the scenes is FEA-derived stresses up here in geometry are being combined with varying load here. And you can imagine that if FEA says, how does load become stress? And then now we say load changes over time. This calculation engine here, this design life fatigue lift, is actually looking at how does stress vary over time, not for 5 locations, but actually for every single part of this model, every single node or every single element. So I can take a look now, and this plot, let me just zoom in here a little bit. We can get a little better look. Actually, I'll make this bigger, be easier to see. Okay, so what we have here now is, this is our contour plot in fatigue life. This is our contour plot in fatigue life. So what design life has brought to the table for us here, what this calculation has done, is it's allowed us to look past FEA for stress and now look at fatigue life contour plots so we can head-on address this fatigue failure mode and answer the question of, will our redesign meet our life target? I'm going to add a couple of labels to this. We call this hotspot detection. Bear with me just a second. I'm just going to reconfigure this display a little bit. I'm going to put a couple labels on our picture here, like this. And so what I've done now, I've just added some callouts that say, in these certain areas down here, what are the fatigue lives? And you can see, either based on the legend here or by looking down this way, this is our critical spot right here. And it's got a fatigue life of 45,000 repeats. Again, 45,000 laps. So the beauty here is that what I've done is, through this analysis, I've, number one, been able to assess before going to production, was the previous part going to survive? And sadly, the answer was no. But we took that that negative judgment and turned it into a positive by saying, let's redesign this. And we have stress guidelines, stress reduction guidelines. We said 15, 20, 25, whatever percent. Part was redesigned, and now virtually we can come in here and take a look very quickly at this. Will this design pass or not? In other words, is it worth committing prototype resources to? In our case, the answer is yes. So first part didn't pass, but we've intelligently redesigned with the fatigue failure mode in mind, which allows us a way forward to meet the structural durability requirement of that particular part. So that was a little hands-on, and if you want to know more about how to use nCode software like this, please take a look on ncode.com/webinars, and you'll see many other webinars that are much more software-focused than today's. So in summary, here's the agenda. Wait, hang on. Why are we doing the agenda at the end? Because this is the part where we review what we talked about, okay? So we started today by asking the question, what is fatigue? And we defined it as a progressive damage accumulating failure mode. So another failure mode we need to design against if our part sees varying stresses. Secondly, we looked at an overview of a couple different fatigue methods, the stress life method, the strain life method, and the crack growth method. And we saw that the stress life method has been around for a long time, works well for high cycle fatigue, but has serious limitations due to its linear elastic material model in low cycle fatigue. Strain life, being a bit newer, and when I say a bit, I mean as in having been developed in, say, the last 50 years, brings to the table a nonlinear material model and therefore can understand both low cycle and high cycle fatigue. And lastly, we talked about the crack growth method, which is great for once we have an engineering macro crack, how much time is left or how many cycles are left before fast fracture occurs. We looked at how do we apply these methods in either in using strain gauges, measured strain data, or by using finite element derived virtual stresses and strains. We did a quick case study just to show how an engineer might take these concepts and put them into action.